Well, you've been working your way through the playlist here. I first want to commend you on getting this far. These have not been an easy set of questions, but hopefully they seem more doable once we get through them. So the good news is you're almost done. The bad news is we've got question number 6, and this is our series question. So looking into part A here, they talk about function f having derivatives of all orders within that interval from -1 to 1. Not really important to us, but they've got to say it. The derivatives of f satisfy all these conditions above, and the Maclaurin series for f converges to f as long as the absolute value of x is less than 1. Basically what they're saying there in that last little statement, and this is not paramount to us, but when they say it converges to f for they're basically saying that the interval of convergence is from -1 to 1, and the radius of convergence is a positive 1. But I don't know if that's going to play much of a role in our solutions here today. To me, the most interesting thing by far is this definition right here. They're saying the n plus first derivative is equivalent to -n times the nth derivative at 0. So, for instance, if you want to find the second derivative, we're going to have to let n equal 1. Or if you want to find the third derivative, we're going to have to let n equal 2 and so forth. So we're going to get into that. And again, question A, they're basically saying, hey, let's show that the first 4 non-zero terms in the Maclaurin series are equal to these 4 right here, which is really nice because you kind of got this insurance plan of here's what the final answer should be, and I got to just kind of fill in the gaps and connect the dots. So let's see. So that's the 4th degree polynomial. I'm thinking that the 4th degree polynomial in a general sense is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial times x cubed plus, we'll squeeze in this 4th derivative at 0 over 4 factorial x to the 4th. So those are the terms that I want to fill in. And what I want to do on the side here is just kind of find all those derivative values, and then I'll kind of sub them in. So we already know that f of 0 equals 0. We know that f prime of 0 is equal to 1. Now, the second derivative is going to be, I'm going to substitute a 1 in for these n's, all these n's up here. So it's going to be -1 multiplied by the first derivative, which is going to make -1. Now for the third derivative, I'm going to substitute a 2 for those n's. So I got -2 times the second derivative, which makes +2. And then we got to go one more. We're going to do the 4th derivative. So it's going to be -3 times the third derivative, which is going to make -6. All right. So I'm going to plug those values that I just got. I'm going to sub them in here, 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 and here. Other than that, pretty much things are taken care of for us here. So let's see if we can put this all together. That 4th degree polynomial is going to be 0 plus, we got 1 times x minus 1 over 2 factorial x squared plus 2 over 3 factorial x cubed minus 6 over 4 factorial x to the 4th. Now, normally I wouldn't emphasize or even encourage you to worry about cleaning up those coefficients, but I do want to simplify them in this case to prove that this answer is equivalent to the polynomial they gave me at the beginning up here. And I think we're all set there. All right, so what does part B look like? Determine whether the Maclaurin series, oh, did I forget did they want the general term? They did want that. I almost forgot about that general term. Okay. So when I go to write my general term, let's assume the first term is n equals 1, n equals 2, n equals 3, n equals 4. So if let's just say I kept going here. We do have an alternating series. Now in this case, if you want the first term to be positive, we're going to raise it to the n plus 1 power. And then from there, you've got x raised to the n divided by n itself as your general term. So let's say I took that general term and I wrote it as a series. So I've got the summation from n equals 1 to infinity. We've got -1 to the n times x to the n all over n. They said if we let x equal 1, will this series converge absolutely, converge conditionally, or just flat out diverge? So let's see what that's going to look like. If I plug in a 1 for x, I get the alternating harmonic series. Now, this alternating harmonic in and of itself is going to converge by the alternating series test. So I can rule out this answer right there. It's either going to converge absolutely or converge conditionally. Now, what you want to do now is you want to take the absolute value of that expression and analyze this one. Now, this is the harmonic, and he diverges. And you could just refer to it as the harmonic. That's acceptable on the AP exam. Or you could talk about how, well, it's a P series and P equals 1, and therefore it diverges. But the nutshell is, if this guy diverges, we're going to go back up here and say that that series, -1 to the n over n, converges conditionally. In other words, the only reason it converges is based on the condition that it's alternating. And if it wasn't alternating, it would diverge. That's basically, in a nutshell, what converging conditionally means. All right, part C. What we're going to do here in part C is we are going to, we'll go with that color. All right, g of x is the integral from 0 to x. Now rewrite f of t, basically your answer from part A in terms of t. So it's going to be t minus 1/2 t squared. Notice I could have written t squared over 2, but when it comes to integrating, I just prefer, just a slight preference there to rewrite it like that. And I'll go 1/3 t cubed minus 1/4 t to the 4th. And then we've got our general term here, -1 to the n. 1 over n is the coefficient, x to the n. I'm not sure why I put parentheses around 1 over n. And then we're integrating with respect to t. Okay, so let's say we integrate this bear. We're going to get 1/2 t squared minus 1/6 t cubed plus, let's see, what would that coefficient be? 1/12 t to the 4th minus 1/20 t to the 5th. So just using some real basic integration there with the power rule. Now here's where it's easy to get hung up on this general term. I'm going to get 1 over n times the quantity n plus 1 is the new coefficient, x to the n plus 1. And all I did right there is I'm integrating. I'm always adding a 1 to that exponent. That's how I got n plus 1. And then I'm basically dividing that term by the new exponent. And that's why you see an n plus 1 in the denominator. So if we just go through and substitute an x for all of those t's, we're going to be done. We're going to be in good shape. So it's going to be 1/2 x squared minus 1/6 x cubed. This makes for a really exciting video, I'm sure, here. Bump, bump, bump. And let's say -1 to the n divided by the quantity n plus 1, x to the n plus 1. And that is our g of x function. And you know what? If I'm going to say g of x equals, I might want to put a ... there in the end. All right, we're cruising. And I think part D is going to be really nice. Well, I don't want to jump the gun. So if you recall, we did have an alternating series back here. You see the first term, we went from a positive to a negative to a positive to a negative. So we do have an alternating series. And basically they're saying if we were to let x equal 1/2, could we guarantee that the error bound is less than 1 over 500? Now, when it comes to the error bound of an alternating series, it's all about the first omitted term. Or sometimes we say the first neglected term. And in this case, the first neglected term, you see right here, I'm going to put a little arrow. See how you're using a 4th degree polynomial? The first omitted term is going to be the term that has the x to the 5th in it. So let's go back up here and look at our answer. All right. So let's say, let's switch colors here. Okay. Everything from here to here is considered p sub 4. That's your 4th degree polynomial. So right here is your first omitted term. And basically we're looking at the magnitude or the absolute value of that term. So let's shimmy down here. We'll say our first omitted term equals, oh boy, what was that term? X to the 5th over 20. If we let x equal 1/2, that's going to be 1/20th times 1 over 32. And that's going to make 1 over 640, which is less than 1 over 500. And therefore, we could guarantee that the error, or the difference between the exact value and the approximation, is going to be less than 1 over 500.